So fam, this is the overview for Unit 1. As I was going through and doing this overview, I realized that for lots of you guys, you're probably going to need more space than this. So as you're going through and doing your review materials and your mini exams, if there are things that you need from Unit 1 that aren't on this overview, you should start adding things to the back of these overviews, because remember, the plan is that the weekend before your exam, so your exam's on a Tuesday, starting on like Saturday, Sunday, Monday before your exam, really the only thing that you guys should be worrying about and going over and studying are these overviews. I mean, you might want to look through your problems. You might want to try one of your practice quizzes that weekend right before your exam. But when it's time to study, I think one of the most effective ways that you guys can study is have these overviews available and just remind yourself of the information that we have learned so that it's fresh in your mind when you go to the test. So these overviews, 1, are to remind you of what we did in each unit, and then 2, they are a good snapshot of what that unit is about so that you can keep it fresh in your mind right before you test. One other thing, this is not the only overview that we have for Unit 1. So I did give you a piece of cardstock that's all about describing data, because anytime you're asked to describe a distribution, they want you to do SOCs, so shape, center, spread, outliers. So notice the heading of this is describing the distribution of data. They want you to tell them, what is the shape of the data? Are there any unusual points or outliers? What is the center? Should you use the median or should you use the mean? And then spread. Should you use the range or the IQR? Then if I flip to this back side, it actually goes through and gives you an explanation of each of the things that I have on the reverse side. So what is not included on this overview is this idea of shape, center, spread, outliers, because you have a sheet for that. So you need to remember that median is resistant to outliers. IQR is resistant to outliers. Mean is not. Standard deviation is not resistant to outliers. Range is not resistant to outliers. So you want to make sure that you go through these sheets to remind yourself of shape, center, spread, outliers, which measures are resistant, which ones should you use if your data is nice and symmetric, and which should you use if your data is not nice and skewed. So, along with this overview I'm about to go through, you want to keep in mind that you have this paper on describing the distribution of data. I'm not going to talk too much on this overview. I want you to be able to take from it what you need, but not be stuck with me forever. So starting at the top, one of the most important things to recognize is that there's 2 types of data. You have categorical data and quantitative data. Categorical data is literally categories. So you describe your different categories with words. So categories like yes or no, agree or disagree. And then I have C examples below. So here you can see your categories are type or genre of movie. Here it is your recommended diet, so different food groups. Here it is frequency, so are you a heavy smoker? Have you never smoked? Here it's do you own a cell phone? Yes or no. And then underneath here it is the revenue, expenses, and profit or loss. So as you can see, all of the categories on this left-hand side of our paper, in fact, maybe I should blank out the right-hand side, are all words. So for categorical data, everything is words. For quantitative data, it's numbers. So these are numbers that you can find an average for. These are numbers you can find an average for. The other big distinction, and before I move on, sorry, you can see that especially like in your stem and leaf, the plot is made out of numbers. So quantitative is numbers, categorical is words. Either way, no matter what your data is, if you are going to graph your data, you always have to scale and label your X and Y axis. So you always have to label both sides. Also, we don't go through this, or I didn't specifically write down how you can make all of these graphs, but you need to know how to make all of these graphs. So you need to know how to make a bar chart, or a segmented bar graph, or a side-by-side bar graph. You need to know how to make a dot plot, a histogram, a stem and leaf, a box plot. So even though it's not explicitly written on here, you need to know how to make all of these graphs that you see. For categorical data is where we get P and P hat. So we've done tests on P and P hat, we've estimated P and P hat, and we have done confidence intervals for the proportion and sample proportion. So P and P hat come from a categorical data set. X bar and mu, we've done the same things for X bar and mu. So we've estimated them, we've made confidence intervals, we can do hypothesis tests about them. X bar and mu come from quantitative data sets. Then lastly, so we're comparing them at the same time at this point. Categorical data has no shape. You will never do shape, center, spread for categorical data, ever. So you do not do shape, center, spread for categorical data. Quantitative data is the only one that you actually do SOCs for. So quantitative data has a shape. You can describe the shape, and you describe the shape by doing shape, center, spread, outliers. Categorical data has no shape. No shape. You never say that this is approximately symmetric. That's not how categorical data works. So, words, numbers, P, mu. Cannot describe the distribution, can describe the distribution. Either one, you must know how to graph it and how to scale and label your graphs. So that all being said, I labeled what these are. These three things are bar charts. Actually, this is a bar chart too, so I should have drawn another arrow. All of these are bar charts. This is a pie chart. These are two-way tables. These are two-way tables. Pie chart you only use when categories are part of a whole. So you could use a pie chart for this one as well. You could do a pie chart here, but you would have to do 3 separate pie charts. Here you would have 2 separate pie charts. And then here you would also have 3 separate pie charts. When you are given bar charts like these 3, 1, 2, 3, if they don't look exactly the same, so if these two things don't look exactly the same, that means there's an association between gender and how frequently a person smokes or that person smokes. So there is an association between gender and smoking because these two bar charts are not the same. Here, there's an association between the year and your revenues, expenses, and profit because these bar charts do not look exactly the same. In fact, yeah, these are almost the same, but this middle bar is clearly bigger, so there is an association between the year and the income. So there is an association between gender and smoking. There is an association between year and income. Here, we're not looking at association because we're not comparing two groups. So this is just one set of people, what's their favorite type of movie. Here, this is your recommended diet, the different categories. In each one, I tried to identify what the categories are. So the categories here are the year. Just kidding. They're the expenses, revenues, and profit loss. Here, your categories are gender. Like I said, here, their type of movie. Here, it is the different food groups. The one that you use the most often to determine if there's association is a segmented bar chart, and it is related to your conditional distribution. So the last thing to talk about on the categorical data side is the difference between the marginal distribution and the conditional distribution. So the marginal distribution is based off of the table total, and it tells you the percent of each category. So here, your category is yes or no, has a cell phone or doesn't have a cell phone. So over here, across from it, it's telling you 73% of your sample had a cell phone, 27% of your sample did not have a cell phone. So it's telling you the percent in each category. Here you can do it for the age group as well. So this has two different categories. It has yes or no, and it has age groups. So 23% of the people in the sample is 10 to 12 years old. 42% of your sample is 13 to 15 years old. 35% of your sample is 16 to 18 years old. So a marginal distribution tells you the overall percent of your sample for each category. Notice that it's on the outside of your two-way table. Then a conditional distribution is the inside of your table, and it's usually based on the explanatory variable. So if I'm looking at this two-way table and my two categories are age group and whether or not they own a cell phone, your age group will affect whether or not you have a cell phone. Your cell phone does not affect what age you are in, age group you are. So we would base our percents off of your age groups, which means that in order to find these conditional percents, you go across from your explanatory variable and you base your conditional distributions off of each category. So of the age group 10 to 12, 40% had a cell phone, 60% did not. Now here I change it. These fractions or these percents are 88 divided by 110 and 22 divided by 110. So that tells me 80% of the 13 to 15 year olds owned a cell phone and 20% did not. Then lastly, for my age group 16 to 18-year-olds, I do 78 over 92 and 14 over 92. That tells me 85% of my 16 to 18-year-olds do own a cell phone, and only 15% of my 16 to 18-year-olds, do not own a cell phone. So when you make a conditional distribution, you base it off of the explanatory variable. So here, explanatory has 3 age groups. So I base these percents off 60, these percents off of 110, these percents off of 92. Then I just explained what one of these is. 60% of the 10 to 12-year-olds do not have a cell phone. That's what that's telling you. 80% of the 13 to 15-year-olds have a cell phone. Hi, what do you need? Okay. Then, with your conditional distribution, this segmented bar graph is a visual representation of this conditional distribution. So notice this would be 60 and 40, just like from my table. This one would be 80-20. This one would be 85-15. So it is very important to know a conditional distribution can be graphed as a segmented bar graph. That is a ton of information. You have several problems in your review that go over that. Oh, I took my Post-it note off, so I didn't mention this. When you do a conditional distribution and a two-way table, what you are looking for is if there is an association between the two variables or between the two different, I guess we should just call them variables. So when you're describing an association, you want to say there is an association. In general, give specific values. So I have written this up specifically in terms of this cell phone problem. So these are the 3 things that you have to do. Say there's an association, say in general, and give context, and then give a specific value. So that is the response for cell phones and age group. There is an association between age group and cell phone ownership. In general, older kids are more likely to have a cell phone. 85% of the oldest age group have cell phones compared to only 40% of the youngest age group. 13 to 15 is only slightly less than the 16 to 18-year-olds. So when you describe association, you need these 3 things. You need to say there is an association. You need to say in general, ... and you want to say more or less likely if you can. Then you want to give specific values from your segmented bar graph or your two-way table. So, yeah. The only thing that maybe I should have added here is that the segmented bar graph shows there is an association between age group and cell phone ownership. I should refer to my two-way table or my segmented bar graph when I do that. So here you should refer to your two-way table. Or bar graph. Remember, you don't always have to use a segmented. If you like the side-by-side, either this one or this one, you can use that. Okay, that's it for categorical data. If you get stuck on marginal and conditional distributions, you're going to want to really draw it out on the back side of this, because this is not one thing that you can let go of. So often in class, I'll tell you, like, if you don't feel good about this particular thing, then just forget it and focus on other things. This is not something that you're going to want to just forget it. You want to make sure that you can do a conditional and a marginal distribution. It's very, very important. Oh, that's not what I meant to do. So sorry. I meant to make myself little, not the doc viewer. Okay, then this other side, we've talked a lot about this other side, so just make sure that you remember that histograms do not give specific values, and typically it's the left-hand side that's included. So for this first class or bin, it includes 60, but not 65. This one includes 65, but not 70. So the lower bound for each bin is included in that interval. These two things can look similar. So the advantage is that you can see the actual data values in a stem plot, but you can't see them in a histogram. A dot plot is the easiest and in most cases the quickest graph to make. And remember, in a dot plot, your y-axis is count or frequency. So 2 people had no siblings. On this one, this does look similar to a histogram, but the shape, you can't see the shape very well. In order to fix that, you would want to do a split stem plot. So notice here I've written, this allows you to see the shape better. So for this one, I would bet that if you broke it up into a split stem, the shape would look way better. This one, it doesn't really do a whole lot, but it does show you that there are like 2 different groups here. You have like a bunch of data from 0 to the lower one, and then a bunch of data from 2 to the lower 3. So this graphic is just reminding you how you would split stems, and it's also reminding you that it's so that you can see the shape better. Remember, you must always include a key when you make a stem plot. Then lastly, for the stem plots, you could make a back-to-back stem plot when you are comparing 2 distributions. So dot plot, quick and easy. Histogram, I personally think the most complicated, but also one of the most common. Stem plots, you have a lot of options. Regular stem plot, split stem plot, back-to-back stem plot. Remember, you have to know how to make and analyze all of these. And by analyze, I mean describe specifically with your shape, center, spread, outliers. Then lastly is your box plot, which we have used quite a bit in the confidence intervals and hypothesis testing units, so hopefully you feel good about these. Remember, your box plot is your 5-number summary. It's a visual representation of your 5-number summary. This is just showing you what each of the elements are. So it's breaking down what each part of the box plot is. You could have side-by-side box plots, and if you have them, they're typically asking you to compare them. So here you can see that I've written, make sure that you can compare distribution. You're going to use SOCs and comparing words, meaning the median for river X is greater than the other medians. So the concentration for river X is typically greater than for Y and Z. And then I have that written down here. Based on the medians, river X has a higher concentration than rivers Y and Z. So this is reminding you, when you make comparisons, whether it's for a stem and leaf or it's for a box plot, you need to use comparing words and do socks. So this side didn't take me nearly as long to describe as the categorical side because we've been dealing with these for almost all of the course. We don't talk much about two-way tables after this unit, but these graphs we do see. Socks applies to only these graphs. If you're asked to describe data, they want you to talk about socks. Know how to make them all. Know how to compare them all. Anything that you need from this unit that is not included on this page or your socks page, you need to write on the back of this. You will absolutely 100% have to compare distributions on this exam. You will 100% have to describe if there is an association between two variables. Association is different than scatter plots. Scatter plots is two quantitative variables together. So an association here is different than the association that you see in a scatter plot. I know that that's a lot of information to take in now, but it is essential. This essential. Comparing distributions, you must know how to do. Socks, you gotta remember socks. Okay? Okay. Love ya.